at this point, we are coming to the second section of this today's course. So we are going to define the concept of covariance. What is covariance? And before that, before explaining covariance, let us remind ourselves with the expected value and variance, the definition of expected value and the variance. Now, if you remember, we were defining expected value and the variance concepts for giving us partial information about a single random variable. The expected value gives us information on the central tendency of a random variable. So on the, what is the average value of this random variable? What is the mean value? So expected value is this. Around which value the possible values are distributed, okay? So average value, the mean value is the expected value of that random variable. And the variance gives us information on the dispersion of a random variable. It is a measure, variance is a measure that gives us information about how dispersed the possible values of this random variable over the real line, or how they are spread, okay? So if the possible values are taking too many values over the real line, which are too distant from each other and which are distant from the average, then we say that the variance of that random variable is large. However, if the possible values that the random variable can take are very close to each other, even though they are different, they are very close to each other, then we say that the dispersion or the variance is small. But you see, the expected value is a measure of central tendency, and the variance is a measure of dispersion defined for a single random variable. Now, covariance is not defined for a single random variable, my friends. It is defined for two random variables, and the covariance gives us information about the dependence relationship between these two random variables. So it is a measure of dependence. It gives us information on the type of dependence on defined between two random variables. Now, let's see how the covariance is defined. Now, if you remember, so let me show you. If you remember, the variance of x, is equal to what? It is equal to the expected value of the squared deviation of the random variable from its mean, right? From its expectation. So the expected value of the squared deviation from the mean is called the variance. If you remember this is the definition of variance. Now, I had to write this down because I would like you to remember the definition of the covariance. The covariance between two random variables, x and y, is defined as the expected value of the product of respective deviations from their mean. So x minus expected value of x is called the deviation of random variable x from its expectation, and y minus expected value of y is again the deviation of y from its expectation, and you multiply these two values, and the expected value of the product of these deviations is going to be called covariance, okay? So instead, I mean, in the ordinary variance that belongs to a single random variable, we were just taking the square of the deviation, right? So here, we are writing down both deviations and we multiply them. That belongs to respective random variables. Now, the covariance formula can also be transformed into another form, which is much more convenient to use, just like for the variance. So remember, the variance of x is also equal to what? It is equal to expected value of x square, minus the square of the expectation, right? Now, similarly, I can also determine the covariance of xi by transforming the classical definition into another form, and it becomes expected value of x times y minus expected value of x times expected value of y. So instead of expected value of x squared for the variance formulation in the covariance, we have the expected value of the product of these two random variables, and we subtract the product of the individual expectations. So instead of instead of expected value of x squared, we have expected value of x times y. And instead of expected square of the expectation, we have the product of individual expectations. Okay. Now, how come this classical formula can be rewritten in this convenient formula? I mean, basically, you are going to multiply these two deviations with each other, and what you would get is x times y, the product of the first terms, minus x times expected value of y. So the first term from the first component times the second term in the second component, minus we have expected value of x times y. Finally, the last term here will be the product of the last two components. And then you can rewrite the expected value of the sum of these four components, even though we have negative signs in between them. It doesn't matter because subtraction is also a kind of summation with a coefficient -1. Therefore, we have expected value of the first term minus the expected value of the second term minus the expected value of the third term plus the expected value of the last term. Now, every expectation inside the other expectations are going to be considered as a constant value because they are not conditional expectations. They are just ordinary expectations. These ordinary expectations can get out of the outer expectations. Therefore, in the second and in the third term, we will see minus expected value of x and expected value of y. And in the last term, we have two expectations inside the expectation, and both of them are considered as coefficients. They are simply constants. So the outer expectation does not make any sense because inside there is no random variable. So we can write everything inside exactly the same. And because of that, the last two components will cancel out, which is minus product of the expectations plus product of the expectations. Therefore, all that remains is the expected value of the product minus the product of the expectations. So we have two different type of formulations for the covariance, the classical formulation and the convenient formulation. Usually we use this convenient formulation much more frequently. Now, let's just say we are going to calculate the covariance between two random variables according to this formulation, and we are going to practice this in a few questions, but after the break. But before that, let me conclude that unlike the variance, the covariance can get negative values as well. I mean, in the variance, so if you remember the variance definition, it is the expected value of the squared deviation, and the squared value of anything, the squared values are always positive or zero. So they are non-negative. Therefore, the variance can never be negative. However, this is not the case for the covariance. So covariance can be positive or negative. In fact, it can be zero as well. So when the covariance is positive, we say that there is a positive dependence relationship between x and y. Or in other words, we say that when x takes high values compared to its average, then y tends to take high values as well. For example, let's just say x is the first midterm grade of a student and y is the second midterm grade of the same student. Now, if the student is successful, then both midterm grades can be great, okay? But if the student is lazy, most probably both the first and the second midterm grades are going to be low. So it depends on the student. Therefore, we say that the dependence between the first and the second midterm grade of the same student is a positive dependence. If one of them is high, then the other one is expected to be high as well. However, there are random variables which have negative dependence relationship as well. And for these random variables, the covariance is going to be negative. For example, if x is the odometer value of the second-hand automobile, and if y is the second-hand price of the same automobile, then if the odometer value is high, we expect the price to be low, right? Or vice versa. If the odometer value is low, we expect, because the automobile is not used very much, the expected value is going to be, the expected value of the price is going to be high. So therefore, there is a negative dependence. If one of them goes down, the other one increases. there is a negative dependence between these x and y values, and therefore its covariance should be negative. So the covariance, by looking at the covariance values, we can decide about the type of the dependence relationship. And we are going to practice this after the break. So I am going to stop recording.